Somebody pointed out yesterday, quite sharp-eyed, that in question 1, which is the kind of question that I was doing yesterday, I haven't actually given a value for VCE SAT. So to do it by the way I did it in the lecture yesterday would be very difficult because you'd have to make a choice to answer the question. And all the answers that I've got on this sheet don't include that value. So for the sake of argument, we'll say that VCE SAT in question 1 is 1.1 volts. If you want a value to use for that question, then that would be sufficient. So on to the material of today. This is our first lecture on amplifiers, and I've given you out some written notes. The outline for this lecture is that we will discuss transistors in amplifying applications, and we will talk about their characteristics that we're interested in, which is gain, input and output impedance, voltage and current and power gain, and transimpedance and transconductance. And then we will spend a little bit of time looking at how amplifiers actually do the job of amplifying. And we will look at some characteristics with some signals. And then we will develop a value for the voltage, a method of deriving the voltage gain for a simple one transistor amplifier. And then we will make some deduction about how we can simplify the maths that we need to do. And once we've done that, we will look at a tale of two biasing circuits. But we'll only actually do one because we'll run out of time, so the other one will be next Monday. Oh, is it really going to take this long every time? Right, what's on the next slide? That will change in 10 seconds or so. In the meantime, so if I had a question which said define an amplifier, a good set of words would be an electronic component circuit or subsystem which can accept an input signal and output it at a higher power level with minimal distortion. There it is. So this is different from a transformer, as I said some time ago when we started transistors. With the transformer, if you put in a certain voltage and you have a certain ratio of voltages between input and output, say it's a half, so you put in 10 volts, you get out 5. If the circuitry that you're loading your transformer with draws an amp, you'll be putting in half an amp in order that the total power going in should equal the total power going out, with the exception of some small losses which I haven't considered. The amplifier is different in as much that the signal going in has less power, or can deliver less power to a set resistor than the signal coming out. And the way that we achieve that is essentially by modulating the DC power supply which the transistor is running off. So what we're doing is we're taking some energy from the DC power supply and using it to drive the load. So there is a certain amount of detachment between the input and the output. So there are 3 figures of gain for amplifiers: the voltage gain, current gain and power gain. Strictly speaking, there are actually 2 more, which is the transimpedance and transconductance. We'll discuss those in a bit, but if you said what's the gain, it would either be defined by the sort of amplifier you were looking at, or the person you were asking would go, which one? That was quick. So if I asked for a definition of gain, or you wanted a definition of gain, gain is the ratio of the output variable, any of those 3, to the input variable, which could be the same. So gain is not necessarily unitless, although if it was volts out and volts in, it would be. It could be current out and volts in which case it would be 1 over ohms, the units of gain, which would be Siemens. A definition for the input impedance is the ratio of the input voltage to the input current. So you could say, I could blank this, can't I? And some chalk. There's some. Right, so I've got a black box here, which is my amplifier, and there is some internal resistance that I don't know about, and this is going to be my input. We'll say it's voltage input for the sake of argument, and also for the sake of argument we'll say it's current output, because that would probably make it a bipolar transistor. So if I wanted to know what the value of this input resistance was, I could say, well, I can measure the amount of current that's flowing into this node by breaking the circuit and put an ammeter in there if we're actually physically doing it. And if I divide VI by I in, then I'll get the value for whatever R in is. So that's input resistance. Similarly, I could say, well, what happens if I short the input and I try to drive this this output with a voltage. Now there'll be a little resistor in here, which will be our output resistance, and this, you may remember, is a Norton source. It would be perfectly acceptable for me to adjust this so that it was output impedance was done like this, and that would make it a Thevenin source. Much as you can convert this to that by a transformation which was given either in 117 or sometime earlier in the lectures. So if I wanted to know about the value of this resistor, I could say, well, there's definitely some current leading there, but I can try and impose a voltage here, and the overall current will be, the current that ends up going down there due to this minus that, and I can divide through and get R out. So that's what I mean by input and output resistances. And we will, that diagram's in the notes in a couple of slides. So we'll apply Ohm's law at the output and the input, and that will give us the resistances that are there. And an ideal amplifier will have infinite input resistance if it's a voltage amplifier and zero output resistance. But generally speaking, amplifiers are not perfect. So an amplifier must possess voltage gain and current gain in order to have power gain. Voltage amplifiers are of the type like that with the other source, and we use them below 30 megahertz. And the reason is, the short answer is that above 30 megahertz, voltages tend to travel down wires instead of just appear, which is contrary to everything else that anybody will ever say on the matter until they start talking about high frequencies again. Because voltages don't travel, currents travel and voltages are across things, and that's what we've been saying since September. The fact of the matter is voltages do travel down wires, and they travel as electromagnetic waves, and the electric bit collapses and supports a magnetic bit which reappears, and then the magnetic bit collapses and supports an electric bit that reappears, and that's how electromagnetic waves propagate down copper bits through waveguides and in free space as radio waves. When frequency is increasing to the point that the wavelength of that electromagnetic wave is quite similar to the size of the circuit involved, you can no longer think about voltages as just appearing places. You have to worry about how they travel. And when you worry about how they travel, you have to worry about what happens if they bounce off things. Because if you were to look in a mirror, you'll see a reflection of yourself and probably pass some judgment accordingly. But the fact of the matter is, the electromagnetic waves that you're looking at are the same kind that travel down wires. They're the same kind that travel from your brain into your muscles to make your muscles contract and provide locomotion. So in the amplifiers where we have very high speed signals, we have to worry about what happens, and the signals can be reflected in the same way the light bounces off a mirror. And the same way that if you walk between two big buildings, your mobile phone signal probably goes a bit wally because there's a lot of multipath effects. So in the voltage amplifying situation, we will not use it above 30 megahertz, and the difficulty arises because we will assume there is a very big input impedance. Ideally, it will be infinite. And the problem with that is when the voltage wave arrives at the input of the amplifier, it will not see the same impedance that it saw looking back down the wire. So there will be a mismatch, and the mismatch is like a mirror. So the voltage will get to the amplifier and not exactly bounce off, but it will be reflected. And another way of thinking about that is that some of the power that we want to transmit into the amplifier will be reflected as well. So we won't be able to get all of our signal into our amplifier. This will be covered again, and it doesn't come into this course or any course that follows it for a couple of years. But when I say use below 30 megahertz, the reason is because you cannot really use this kind of amplifier with travelling waves. If you're interested, feel free to Google it. So for the voltage amplifier, gain is output voltage over input voltage, which is unitless, and it should have infinite input impedance. That's to say it draws no current into its input terminals. It is a perfect voltage measuring thing. And it should draw, and it should source any current that it needs to into its load. So whatever load you put on there, if you've got a gain of 10 and you put 1 volt in, it should be able to supply 10 volts, even if that means driving a perfect short circuit, so infinite current. Obviously there are no amplifiers that will develop infinite current. Current amplifiers, now for the same reasons that I just gave about travelling waves, you can't use them much above 30 megahertz either. The gain in this case is output current over input current, which is amps over amps, which is still unitless. And in this case we want to, yep, I'm so sorry. You should have said earlier. Right, do say something. That's the slide that's just been missed. Right, current amplifiers used at, where did I get to? Okay, so zero input impedance. So we want to be able to accept any current into our amplifier, irrespective of the voltage that's needed to drive. We should be able to have a very, very tiny voltage across our input terminals, and whatever current we can accept, if it's 0 ohms input impedance, that current will be infinite, even for the smallest voltage. So we're interested in the current that flows in, not the voltage that drives it. Similarly, we ought to be able to have any current leaving, irrespective of the voltage we need to develop across our load to make that current go. So if I had say I had a gain of 2 for the sake of argument, and I had an amp there, I should end up with 2 amps flowing out. And if I put a mega ohm across the output, this amplifier would need to develop 2 million volts to cause that amp to flow. And it ought to be able to do that without breaking a sweat. Now, there aren't that many amplifiers that will be able to manage that feat, so there are limitations on practical current amplifiers as well. So then we come to power amplifiers, and these are used above 30 megahertz, and we use them in impedance matched systems. And when I say impedance matched, I'm back to mirrors again and travelling waves. When the wave is just about to enter the amplifier, it feels the impedance looking inwards, and it has some, it doesn't know anything and it doesn't feel anything, but it knows about the impedance behind it, looking back into the wires that it travelled through. And if they're not the same, that's like a mirror, or a badly silvered mirror. So there'll be a certain amount of reflection. When the impedance that it's coming from and the impedance that it's trying to get into are equal, there will be as much power delivery as we can manage. So that's an optimal situation. If you go back to the very first or second lecture, I did something about power delivery, and I said I had a car battery and about 5 milliohms, and 7.5 kilowatts was the biggest amount of power transferable. It's in lecture 1 or lecture 2. It's the same sort of thing, but I wasn't worried about travelling waves then. So if you really want to think about it, go back and have a look. But it will not appear in any exam, so you don't have to worry about it. Well, it will not appear in any exam I set you. Put it that way. So gain in this case is power in a power out over power in, which leaves us with watts over watts, which is unitless. And the input impedance ought to be the characteristic impedance of the system. And oftentimes that's 50 ohms or 70 or 75. So if you plugged in a satellite dish lately to a skybox or something, there will be 75 written underneath it, underneath the coax that you're plugging in. And the 75 is the characteristic impedance of the cable between your satellite front end and the box receiver. Same goes for Virgin Media or any of that lot. And it should have output impedance equal to Z0 as well. And the reason is if there's an impedance mismatch between the output impedance and whatever comes here, there will be more reflections. Reflections everywhere means input power transfer. So now on to the funny ones. Transimpedance is a sort of concoction of the current input and the voltage output. So we want to accept any current we can, and we want to produce an output voltage which can drive any current it needs to into a load. And these are sometimes called current to voltage converters, especially if you're working on digital to analog type systems, because you take any current in and you produce an output voltage which is proportional to that current times some gain. So current to voltage converter comes from there. And this should have a gain in ohms, because we've got some input in amps, we've got some output in volts. So we have volts per amp in terms of gain. I put in an amp, I get 2 amps out, I've got 2 volts. Got that wrong. I put in an amp, I get out 2 volts, I got 2 volts for every amp. So that's volts over amps is ohms. And these are often used in sort of fibre optic receiver type front end systems. Usually you'd have some fibre optic cable with some light pulses travelling in them, another form of travelling electromagnetic waves. And you'd have some photodiode or some such where you've got some semiconductor and the light goes in and promotes some electrons and holes, or promotes some electrons rather, and the electrons do some travelling about in the semiconductor, and then they induce a current in the external circuit. So that's basically just a regular PN diode for the most part, except that we're not producing a current by forward biasing it. You reverse bias it, put some light in, and the light produces the carriers for you by an exchange of energy between photons and electrons. So we plug our photodiode into our transimpedance amplifier, and that would turn the current that leaves the photodiode into a voltage for us. And these are pretty commonly integrated into pretty much everything that has anything to do with fibre optics. It's got half a dozen of these sat in it somewhere. And you can buy them as integrated modules. The last one that I want to talk about in terms of the kinds of amplifier is transconductance gain. And this is the output current due to the input voltage. And this is essentially what a transistor is. A transistor has, if we went back to the model of the large signal model of the transistor from a couple of lectures ago, broadly speaking it was the same. If you took away the black box and drew a line between there and there, that would be a transistor model. Okay, the current source is upside down, and I've never actually drawn this resistor, but it does exist. The only thing that we're not doing here is we're not saying there are 3 terminals, we're saying there are 4. So this is a slightly more general amplifier than just a regular transistor. In fact, this that node there and that node there are both the emitter. And then that's essentially the same as drawing that line between there and there. And then we've appeared at transistor. Of course, a real transistor doesn't have infinite input impedance, and it doesn't have zero out, doesn't have infinite output impedance either. But we could say if we could manufacture a perfect device that was like a transistor, this is how we draw it out. So moving for a moment onto practical devices as opposed to just types of amplifier that might exist if we were lucky. We have bipolar transistors, MOSFETs, JFETs and valves, and these are all modelled as transconductance devices. So they can be shoehorned into this shape somehow, and we can adjust the component values a bit to take account of the problems that these devices actually face. And the relationship between the input voltage and the output current is called the transconductance characteristic. And it's one of the characteristics that I talked about a couple of lectures ago when we just talked about characteristics. And it's in the handouts that I gave along with that lecture as well. But to briefly recap, the bipolar junction transistor shape is biscuit. Exponential. I'll do it properly first. And the MOSFET. Say again. Say again. Squared. Squared? Squared it is. Afraid so, it's squared. So, how about the valve? So if you're lucky, he might let you dip it in his coffee. Well, what about the valve? I don't expect anybody to get this. Doesn't mean you shouldn't try. No takers? Sorry?
Cubic.
Cubic. It's nearly actually. It's raised to the 1.5. So it's something called permeance, which is to do with the grid spacing and so forth in the valve, times VGS, which is VGK, grid to cathode, raised to the 3/2. And you can go and read about it. There's some very good books on valves in the library if you're interested in that sort of thing. Also, for the valve, you actually have to turn it off by applying a voltage on the grid. Same with the JFET, whereas the bipolar transistor and the MOSFET, you have to turn them on. Okay, enhancement mode MOSFET, not depletion mode MOSFET. So bipolars and enhancement mode MOSFETs have to be turned on, valves and JFETs have to be turned off. So they will be on under normal circumstances. So this is my best attempt at how an amplifier works in graphical form. And what we have is our transconductance characteristic. So this is our input parameter, and this is our output parameter. So we have, I said earlier, it would be voltage input, current output. So we've got volts in, amps out, and what we have is a constant value of VBE, which is the average of this sine wave. So the sine wave is superimposed on the average value. And the average value is going to be in the order of 0.7 volts for a bipolar transistor. And this will yield a certain collector current, and it will be just there. This will be our average collector current, and that will always flow. And we'll call it the quiescent collector current, because it's what exists when there are no signals, and no signals is quiescence. And the small sine wave that I've applied to adjust the value of VBE, the delta VBE height, will yield a similarly shaped delta IC, and this will be our output signal. And if we want it as a voltage, all we need is some sort of current to voltage converter. Anybody for a current to voltage converter? Come on. It is a resistor, yeah. Would you like a biscuit for a resistor?
Yes.
Yeah, you would. Or is it your colleague that would prefer the biscuit? Oh, I see. Right, you better send them down. Yeah. So, didn't realise lecturing would be such an athletic experience. So we have this output signal, and of course, depending on the size of the resistor, will depend how much voltage out for voltage in you get. So we can say already that if we have to drop some of this IC across a resistor, that resistor will come into the gain somehow. So it's not just the transistor that sets up the gain; it will be something to do with the circuit that surrounds it as well. So you could actually draw a similarly shaped graph, or a similar type of graph, where you've got sine wave in and sine wave out, on the output characteristics if you wish. But I prefer to do it on the transconductance characteristic, because I said a couple of lectures ago that transconductance is the sort of mechanism by which all amplifying devices can ultimately be described. And the output characteristic, you can talk about base current if you want to, but that doesn't work for MOSFETs, so I'd rather look at it like this. Anybody want to hear that again? It's fairly important. Nope, okay. So this slide basically says what I just had. A small signal voltage at the input controls a larger signal current at the output. And to ensure a reasonable linearity, the transistor must be biased to pass a constant, quiescent, no signal current. So what I'm really saying there is that this point here, if I was to draw a tangent to that point, it would be something like that. If I were to start down here, and I drew a tangent, I'd have a very, very small range of available swing before I get the the shape of the curve would involve itself in my output signal shape. So what I really want is a nice linear bit across there. And for all of the work that we do, and pretty much all the design that people do with transistors, they assume that they're working in a region where that characteristic can be essentially called a straight line, even though we know it follows the equation for collector current. And the signals are superimposed onto the quiescent point. And the relationship between delta IC and delta VBE is called the small signal transconductance. That's to say, if I go back to this graph and I said I'm going to divide that distance there by that distance there, I'll get a value for transconductance, that's to say amps out, volts in. And if I'm saying that this line is linear, I should get one value to completely describe that line, because it will be the gradient of that line. And a straight line only has one gradient. And that gradient will be called the transconductance, and it will be small signal, because if I went too far, then the line would no longer be straight, and I wouldn't be able to say there's one value. I'd have to choose several values and switch between them at appropriate points, and that would be a large signal problem. So that's where the small signal comes from. And since the collector current expression is not linear, GM, that's to say the small signal transconductance, depends on the choice of quiescent point and on the amplitude of the signal. So if I made the signal really big, you wouldn't be able to say there's one value of GM. And if I moved the quiescent point down here, say, you'd get a different tangent, sort of like that, as opposed to up there where the tangent is more like that. So your choice of operating point will affect your small signal amplification. So large signal things and small signal things are related somehow. Usually we assume that VBE, delta VBE, is sufficiently small that GM is constant. That's to say, a straight line in the region we're interested in. And when we say that, what we're really doing is assuming the circuit is linear. That's to say, the transistor is composed only of characteristics that have straight lines. And we can think about it in the same way as we think about other linear components, like resistors, capacitors, and inductors. Usually, the collector current flows through a resistor, which converts the output signal current into a voltage. And that's the situation we have in this slide. Now, I don't really like this bit. It's very important, so it has to go in, because it describes the relationship between large signals and small signals really well. And it ought to get the gain of the amplifier. But me standing here telling you equations that you could read off the slide, I don't consider that very productive. So I'm going to go jolly quick to get it out of the way. And what I'd really like is for you to look at it at home and convince yourself that the derivation is accurate. So we have some quiescent base voltage. So this is going to be about 0.7, and we have some change in VBE that we'll put upon it. And the change will be equidistant from the quiescent point, so it's a sine wave with an average in the middle. And this will give rise to a current change of a constant value for IC plus the small signal transconductance multiplied by our input value. And for GM, we have delta IC upon delta VBE. Sorry, was that a hand? Or just a stretch? Just a stretch. Fair enough. It's good, I want you to stay awake. If we go back to here, what I'm saying is DIC by dVBE is the slope of this line, which we're calling straight, and that's the small signal transconductance, which is equation 3. So this gives rise to, this will give rise to a change in collector voltage via across the collector to ground of Vs minus IC upon RL. So we're just applying Ohm's law here, and we're saying that we've got the voltage across RL is IC times RL, and the value here is Vs minus the voltage we dropped across there. That gives us VO, and we're going to sub in IC from up here into there, and because of that minus sign, this plus minus becomes a minus plus. Sub 4 into 2 in your own time. And that will yield number 6. And you can break that down to VO, which is output voltage, plus a constant output voltage, plus or minus some change in output voltage, which is about that mean value. And the quiescent output voltage is Vs minus the quiescent collector current times RL, and delta VO2 is the rest, essentially. So that bit turns up down there as constant, this bit turns up down here as having deltas in it. If it had no delta in it, it'd be up here with this one. So you can rejiggle these to give you a change in V out for a change in V in, and the relationship between those two is minus the small signal transconductance times the value of load resistance. So in this bit here, we only have small changes. Okay, I've got big deltas, but the changes are small. We could just say changes if you don't like the idea of small changes. And there are no quiescent conditions. There is no ICQ or VOQ or any of that stuff down here. It's only small signal parameters, which have lowercase letters, and resistor values. So this is quite convenient actually for us, because if we had to spend our lives writing, every time we wanted to write about transistors, we had to put deltas everywhere, it'd be very, very frustrating and we'd get nowhere fast. Fortunately, because the bias conditions VBQ and ICQ and VOQ do not appear in the last equation on that slide, we can find out about the gain of the amplifier without directly considering the biasing conditions. We do have to consider them, but we don't have to put them in our equations. But we do have to admit that the small signal transconductance, the slope of the line on the transfer characteristic, is a function of the quiescent collector current. That's to say, the further you go up that line, the steeper the gradient will become. The steeper the gradient will become, the further down the line you go, the shallower it will become. The other thing we can say is that the gain is negative. If you look at the equation, we've got a minus before the GM. This means the output signal is 180 degrees out of phase with the input signal, so input signal going up, output signal going down. That's output voltage signal. Oh, that's what I said there. So the key thing, or the really key thing here is point 1, and that is that we can do some calculations on our transistor circuits without having to worry about writing deltas out everywhere. And that is a considerable simplification. So let's have a little look at the circuit. I don't want to stand and point at circuits, I'd rather deal with them. Where's the board rubber? Do you think I could? Come here, will you? You know, if I didn't know any better, I'd say the tuition fee should go up because I don't even have a board rubber. Frankly, it's disgusting. You'll be alright for this. Are you ready? Right, okay, good. So the circuit on the slide, which is now gone, is along these lines. Tell me if I draw it differently because I'd like it to be the same, if possible. Anything more than that? Well, there's some signal input as well, isn't there? Anything more than that? No signal input, right. That's yet to come then. What did I give as the voltage? Yeah. Right. What did I give as the resistor values?
R2, R1, RL and RE.
Right, sod that. This will be 10 volts. This will be 1.3k. This will be 2k. This will be 8k. And this will be 4k7. I hope somebody's got a calculator. Righty. So, what can you tell me about this circuit? Anybody come up with anything about it at all? Preferably using Ohm's law.
Transistor into the base will be biased to 2 volts.
Why?
Because it's essentially 10 volts plus D.
Everybody hear that? We're saying that the voltage here across the 2K ought to be 2 volts. And the reason is we've got, ignoring the transistor for a bit, 10 volts potentially divided between 8K and 2K. Now, you are correct. There is an assumption that you made.
But there isn't a resistance in the form of the transistor.
Yes, keep going. And there's one assumption. Yeah? Alright, you can have a biscuit in a bit. What we're saying here is that there is no base current. There is no current going off down there because we've got a current here and a current here, and if you want to call this a potential divider of these two, you must say that this current and this current are equal, and there isn't any going off down there. So we're saying the base current is negligible, and if you look at the problem sheets and the exam questions, oftentimes I'll say something leading like state all your assumptions. That one should be on your list of stated assumptions, unless of course you're feeling really brave and you're going to include it anyway, just the devil may care. So, where are the biscuits anyway?
Yeah.
They're all gone, are they?
No, it's got
They're coupled, one onto the right. You better throw them down here then. Yeah, if we throw it, don't throw it across students. I'm sure I don't have to do a risk assessment. Cheers. Catch. So what did we have as this current anyway? We never really got to the current. Ohm's law on either, well, we'll do 10 upon that plus that and give us the current down there. So it should be milliamp. Fine. So we're saying no current there, and we've got 2 volts here. So what about this transistor? Anything on the transistor? Perhaps someone from over here. 1 milliamp. If you've got a transistor, so if I go back to my, you can't see this yet, but you will soon. I go back up here. Yeah. I said that this value would be something, this quiescent point. What would we have for a 4-bias diode? 0.7. I think you can probably have a biscuit for that. Oh, go on. Up you go. Right, so out to... For those of you who know what faulty towers is, I think that might be my Manuel. Right, don't need that anymore. Where are the biscuits? We can't do too much more. Gone. Can't do too much more of this biscuit stuff. We're running out of time. Send those back, will you? Right to the back corner. So 0.7 across there. So if I've got 2 volts here and 0.7 volts there, what have I got here? Kirchhoff, 1.3. Could you go and sit over there, because that's where the biscuits are? Come on, back, quick. Yeah, send them down to the chap in the jacket. Right. So 1.3 volts here, which is why I picked 1.3 kiloohms, because I knew where I was headed with this when I started. So what's the current in this resistor? 1 milliamp. You basically have a go. So I've got a milliamp there. So if we've assumed no base current, what should the collector current be? Milliamp. Everybody happy that IE must add up to IC plus IB? Yep, righto. If not, it's in Prof. Houston's stuff somewhere about transistors that that's the case. So that in that case, what's the quiescent collector voltage? So the quiescent voltage across this resistor, which I'll call RL for the sake of argument, 4.7 volts. So we have our DC conditions all defined now. There is nothing else that we need to know about this. The only other thing we might like to say is that I could draw some sort of diagram to describe. This axis has no meaning. It's just a mechanism for me to draw out some graphs. So I could say I've got 0 down here. This will be volts, but it's no particular volts. It's just volts. And I've got Vs up the top, which should be 10. And I've got VB here, which should be 2. And I've got VE, which should be 1.3. Is that big enough? Just about? Okay. So, and we said the collector would be 4.7 volts below 10. So what is the voltage just there? 5.3. In that case, I have some quiescent collector current, quiescent collector voltage. Did I call it VOQ in my notes? VCE, right, okay. Yeah, well it is. Oh, hang on. Did I really? VCE should actually be this one here.
Oh yeah.
I think it's VCQ.
No, just VC.
VC, right, okay. So it's voltage on the collector with respect to ground, so just VC. And that will live here, which will be at 5.3. And this is actually quite a nice arrangement of numbers. Is everybody happy how I got to this graph? The thing about the transistor is it has to be in its amplifying region, which for a bipolar transistor is also called forward active or linear. And we can't have a situation where the collector voltage falls below the base, because if we do, the diode which is in here, there's a little diode that lives there, facing that way, it will become forward biased. If this voltage drops below that voltage, almost certainly will switch on. And that means that our transistor will have 2 forward bias junctions, which will put it into switching mode or saturation. And that's no good, because we need an amplifier. So if I put some signals into this circuit now, by driving it with a Thevenin source, there is some maximum value that I can use. And that value will be the value that derives a signal that just about touches the supply and just about touches the point where there is no voltage across the collector base junction, because that's the point at which it's likely to start turning on. We need, say we need 0.7 volts to turn it on. You can't have the collector drop much below the base, otherwise you risk getting into saturation, into switching mode. So, what's that distance there? 4.7. And what's this distance here? 3.3. Is it 3.3?
Yes.
Yes, it is. So I buggered it up, because that number and that number should be equal to each other. Because this sine wave is not linear, it's got extra components. The average value isn't in the middle. All I can manage up here is something like this. So what will this level be at the top of this sine wave? 2 plus 3.3 plus 3.3. 6.6 plus 2 is 9.6? 8.6.
5.3 and 3.3. 2 plus 6.6.
Yes, it's 2 plus 6.6. 8.6. It is 8, sorry, yes. It is 8.6. Who'd have thunk it? So this is at 8.6 volts. And that's the biggest signal swing we can get out, because otherwise we risk forward bias in our collector. That is how that circuit works. Now, I know that I've got a slide here somewhere which you can't see, obviously. I've got a slide here about working out the biasing conditions. And it's full of letters and so forth. All I'm really doing here is what I just did on the board, but the sort of questions that you will get asked, or the sort of things you'll have to do if you're actually designing this sort of circuit, go along the lines of what happens on the board, not what happens on the slide. Although they are equivalent, it's just one is done algebraically. If you like that sort of thing, then it's fine. but I much prefer to sit down, look at the circuit and go, where can I apply Ohm's law? What do I know about my diode junctions? What can I deduce from this? Because that's the skill of the circuit designer. And it's probably the reason why lots of people think analog's a bit of magic, because you have to sit down and go, what do I know? And the first thing they'll often say is, nothing. Right, I think that's more or less all I've got to say actually. Yep. So I introduced some terminology about gain and bias and input and output impedance. And I said that there were 3 ideal amplifiers and that there were 2 others which deal with transconductance and transimpedance. And then I said something about what happens to signals when they're applied to an unbiased transistor. And I showed that biasing allows linear operation by setting some quiescent conditions. And then we derived very swiftly the voltage gain of a simple transistor amplifier with some bias. And I said we could split up the bias and the signal conditions into 2 different sets of equations. And then at the end we went through the first of 2 circuits, or rather we derived the current and voltage for the first of 2 circuits by an example. There he is.